Hey guys, Alexander here, and in this video we will be covering an introduction to the multiple linear regression model as formulated in the matrix form. Firstly, let's remind ourselves of how do we usually see the multiple linear regression model if we're looking at research papers or when we encounter it in social sciences or in various statistics or econometrics classes. Usually, we will see it as the summation of a bunch of regression parameters or regression coefficients multiplied by the data. So we will have beta 0 plus beta 1 times x1 plus beta 2 times x2 all the way up to beta p times xp. And this is usually the scalar form or one of the simpler forms in which we see a multiple linear regression model being formulated as. This is our intercept. And then all of these parameters become our slope coefficients. And typically, you'll see this in an econometrics class in your undergraduate level studies. Now, this is for the whole model. So we're fitting all of X1's data, all of X2's data, and we're fitting a slope on this. We're fitting an equation onto to try to model Y. But now instead of it just being y equals beta 0 plus beta 1 x1, we are fitting a multi-dimensional equation here. So we can see we're going up to p. So we've got p plus 1 regressors if we include the intercept coefficient over here. But when we look at an individual row in our data, we will see that yi is equal to beta 0 plus beta 1 xi1 plus beta 2 xi2 all the way summing up to beta p xip for I equals 1 to n. And this 1 to n is because we have n samples in our data set. So n samples of data. The I is going to refer to our first row if it's I equals 1, our second row of our data, and these will be the columns x1, x2, x3, all the way up to xp if we have p of these features that we are interested in our data. When we are looking at an individual row, the subscript is yi is equal to beta 0 plus beta 1 xi1 plus beta 2 xi2 all the way up to beta p xip for I equals 1 to n. So we can see that we have got this for our data, we have got x being just the data. If we look at the data, we're going to have x1 over here, x2, all the way up to xp. And we have got n such rows. And this is for our regressors beta 1 to beta p. But we see that we have got a slope intercept here. So that's why we need to, when we're doing the design matrix X, we have to go include another column that is a column of ones to be able to capture this intercept, the intercept coefficient. So let's get started with that. Similarly to the linear regression model, the formulation for the matrix form of the multiple linear regression model is y is equal to x times beta plus epsilon, where x is a matrix, beta is a vector, and epsilon is a vector, as well as y. So if we were to go and look specifically at this model, we will have y being the vector of all of our dependent variables. So y is a vector of all of our dependent variables, and we've got n such values, y1 all the way up to yn. This is what we're trying to model. We're trying to model y by looking at x and how x behaves, and we're going to fit an ordinary least square estimators on it. So x is our design matrix, and as stated before, similarly to the simple linear regression model, your first column is just going to be a vector of ones. We're just going to have ones all the way down n such ones. And then we are going to have, this will be our column for x1, x2, all the way up to xp. But we need to be aware that this is going to be xi1, and specifically since we're in the very first row, So this is x11. This is going to be x12 all the way up to x1p, because this is the formulation that we're using. We're using xi1, xi2, where I denotes the row in which we are working. So similarly for row 2, it's going to be x21 for row 2, column 1, x1, row 2, x2's variable, all the way up to x2p. And the very last row, it's xn1, x2, xn2, and up to xnp. Now this is the design matrix. We call this the design matrix. And as we can see, this design matrix, we have n rows, and our number of columns is equal to, we've got p of them for our features and one of them for the intercept coefficient. So that's n times p plus 1. And then we're going to have our matrix beta, which is the matrix of our coefficients, the intercept and the slope coefficients. And they are going to be beta 0, beta 1, all the way up to beta p. So we see that there are p plus 1. So this is beta, which is a vector of all of our individual coefficients for our regression model. And it's going to be a vector with p plus 1 rows and 1 column. So if we multiply x times beta, then we need to check that the dimensions correspond, and they do indeed do so. We have p plus 1 columns for the design matrix, and we have p plus 1 rows for the vector beta. So that means that if we multiply x by beta, the resulting vector or matrix, or in this case it's a vector, it's n by 1, it's going to have n rows and 1 column. So x times beta is a vector with n rows and 1 column. And lastly, we need to talk about our error terms. So whenever we fit a regression model, we are going to have some residuals, or we're going to have some error terms present. And we've got error terms as well over here. And we have got n of them, n error terms, because we have got epsilon 1, epsilon 2, all the way up to epsilon n. This is an n by 1, this is an n by 1, and this matrix over here, the matrix x beta multiplied out gives us an n by 1 vector as well. So we can see that the dimensions correspond to everything, everything works out. So y equals x beta plus epsilon is the matrix formulation of the multiple linear regression model, where x is your design matrix, beta is your vector of your coefficients in your regression model, epsilon is the vector of the error terms in the model, and y is your dependent variable. So let's carry on to actually calculating the slope coefficients as well as the intercept coefficient for the multiple linear regression model. The formula still holds that beta hat is equal to x transpose x inverse multiplied by x transpose y. This is the most important equation for you to memorize, because this is the case for simple linear regression, SLR, or for multiple linear regression. This formula still holds. It just becomes more difficult to do it in multiple linear regression. So x transpose x inverse, and we need to multiply that with x transpose y. And then that will give us beta hat. And I'll come back to that in a later part. Before progressing to calculating the coefficients for our regression model, we need to first mention the error terms and the sum of squared errors, or the error sum of squared. Epsilon hat, which is the vector of our fitted model's error terms, this is equal to y minus y hat, where y is our actual observations of the dependent variable, and y hat is the vector for the fitted observations. So this is how we will calculate epsilon hat. The sum of squared errors, or the error sum of squared, is given by epsilon hat transpose multiplied by epsilon hat. And this is our error sum of squares. And when we're trying to fit our regression model, our goal is to minimize the error sum of squares, which is the same as minimizing epsilon hat transpose times epsilon hat. So we will take the derivative of this function with respect to our various regression coefficients. So epsilon hat transpose epsilon hat can also be written as y minus x beta hat transpose multiplied by y minus x beta hat. So y minus x beta hat is the same as epsilon hat because x beta hat is y hat. And we are going to take the partial derivative of this function with respect to the vector beta hat. And in the end, what we will obtain is that to minimize the SSE, the solution we get is that beta hat must be equal to x transpose x inverse times x transpose y. And you need not derive this. I will just give this solution to you over here as a stated fact that you need to accept. So we are minimizing our error sum of squares by setting beta hat equal to this formula or this equation over here. And that's the same story and the same approach that we used for minimizing the sum of squared errors for the simple linear regression model, and to actually then derive the coefficients. So that's why beta hat is equal to x transpose x inverse times x transpose y, whether we're talking about the simple linear regression model or the multiple linear regression model. We're just going to talk about a model where we have x1 and x2 as our features in our regression model that we're interested in. So we've got x11, x12, x21, x22, x31, and x32. So if this is x, then x transpose is going to be swap the rows with the columns. So row 1 becomes column 1. You've got x11, x12, 1, x21, x22, then 1 again, and x31, x32. So x transpose x times by x. If we look at the very first entry in the column, it's going to be row 1 times column 1. So we see 1 times 1 plus 1 times 1 plus 1 times 1. This is going to be 3. And 3 is n. So we've got 3 samples because the number of rows is 3 rows. That means n is equal to 3. So always for the matrix x transpose x, the very first entry is always going to be n, the number of samples of data that you have. So if you were only given x transpose, and you were only given x transpose y, so if we have the matrix x transpose x, then this first entry, the first row and the first column's entry, that's always going to correspond to n, the number of samples in your data. If we look at the first row and the second column, we see that we have row 1 times column 1. So this is going to be x11 plus x21 plus x31. And we can see that these are all the values for the first column. So this is the summation of xi1. So this is the same as n x1 bar. So if we wanted to get x1 bar, we would just take this entry and divide it by n that we find over here. Similarly, the second x value, or the third value in this column over here, this is the summation of xi2, because we can see that we have row 1 times column 2. So we have x12 plus x22 plus x32, and that's the summation of xi2. Or we can also say that this is nxi2 bar. And If we know this, then we can very easily, from the matrix X transpose X, derive X1 bar and X2 bar, and also see what the value of n is. And if we look now at the diagonal terms, or specifically the terms in this main diagonal, we will have row 2 multiplied by column 2. So we will have x11 plus x11 squared plus x21 squared plus x31 squared. So we have the summation of xi1 squared. And here we are going to have the summation of xi2 squared. And we can see that this matrix is going to be symmetrical, is going to be a symmetric matrix, because if these entries are going to be the same as these ones over here, let me just show you why. So row 2, column 1, it's the summation of, it's going to be x11 times 1 plus x21 times 1 plus x31 times 1, which is exactly the same as this over here. So this matrix is a symmetric matrix, even though it's the multiple linear regression model. So if you have these results, then you can comfortably work out what the summation of xi1 is. You can work out x1 bar, x and x2 bar. It should be nx2 bar. So that's what the matrix X transpose X can tell us. Now the matrix X transpose Y, we have already got X transpose here. So it's 1, 1, 1, x11, x21, x31, and x12, x22, x32. And Y. So Y, since we only have n equals 3 samples, we've got Y1, Y2, and Y3. So X transpose Y, we've got 3 rows times 3 columns, and another one, a vector multiplied by a vector with 3 rows and 1 column. So we are left with a vector with 3 rows and 1 column. So let's go look at what the entries are going to be for X transpose Y. The first one is going to be row 1 multiplied by column 1. So we have 1 times Y1 plus 1 times Y2 plus 1 times Y3. So this is just the summation of Yi, and that is equal to Ny bar. So Ny bar. If we have then the matrix X transpose X's first entry n, then we can clearly work out that Y bar is equal to the summation of Yi over n. And or if we denote it in matrix form, Y bar is equal to X transpose Y's first entry, the first row and the first column, or just the first row because it's a vector, divided by X transpose X's first entry in the first column. That's always going to be Y bar. The next row is the summation of x11 times y1 plus x21 times y2 plus x31 times y3. So we can see that this is the summation of xi1 times yi, and this is from I is equal to 1 to 3. And the next one we have the summation of xi2 times yi. So here we're dealing with x1 multiplied by y1's entry. The second one we're dealing with the specific x2 entry multiplied by y2. So these are all of the things that are involved in calculating the entries for X transpose Y. So X transpose Y, if we have 3 samples, or if we have a regression model that always has two features, X1 and X2, a multiple linear regression model with X1 and X2 being the features, then we're going to have the summation of Yi, the summation of Xi1 Yi, and the summation of Xi2 Yi. And these values you can use to calculate various other things, but the most important things you need to know from X transpose X and X transpose Y is that they are similar to the formulation that we had for the simple linear regression model, and that we can retrieve the entries for various values directly from these matrices. So if you were only given these matrices, you can go and work out, well, what was the number of samples that we had, which is n, or you can go work out, well, what was the mean of x1, and it's simply this value divided by n. What was the mean of x2? You would take this entry of the x transpose x matrix and you would divide it by n, and you can work out what y bar was by taking this value, the summation of yi, and dividing it by the x transpose x's first entry. So that's just an example of how we can actually use the formulation of the multiple linear regression model in the matrix form, and what the specific and important results are from the matrices x transpose x and x transpose y. And I hope that this video has helped you ease you into the multiple linear regression model and made you see the importance of the matrices x transpose x and x transpose y. The last bit of comment is that we remember beta hat is x transpose x inverse times x transpose y. So you would have to take the inverse of this matrix and then multiply it by this one to actually get beta hat. And that's going to be beta 0 hat, beta 1 hat, all the way up to beta p hat. But most of the time, if the dimension of this matrix, if the number of rows or columns are too great, then they're not going to ask you to do the inverse by hand. They will give you the matrix x transpose x inverse, and they'll just ask you to multiply it with x transpose y. Thank you very much for watching. Boer Commander out.